continue B part 6, exterior algebra, lecture 15a, covariant derivative of the two-form d omega. Omega is one form, as we derived on the previous lecture 14. Now, to derive the covariant derivative of the two-form, given in terms of components, we follow the same general method used for computing the covariant derivative of a tensor, in this case one form. See previous lecture 14. The same steps. Now, step 1 is starting from a scalar expression involving the tensor. Step 2, taking a partial, in this case, take a partial derivative of the scalar, which is coordinate invariant. You see, a scalar does not have direction. You see, that's this change only with the point. Okay, you change the point, you change the scalar in general. And this third one, okay, this 3 and 4, the steps 3 and 4, will be, I will show on lecture 15b, okay? Now then, in lecture 15, in this case, okay, lecture 15b is use Leibniz rule and Christoffel symbols for identify the expression for the covariant derivative of in components. You see, that's what I want to show, just to derive the covariant derivative of the two-form d omega. So let's follow step 1. Scalar built from, in this case, a dw and the vectors. You see, this is I will present the scalar as involving dw and the vectors. Let omega be a one form with the local components omega j, okay, and the omega its derivative, a two form with the components. You see, now this is a skew symmetric property, okay, of the wedge. You remember that, so you recall that. So the omega ij is partial I omega j minus partial j omega I. Now we define this scalar. You see, this actually, I would like to show this is better. So this is the inner product, okay? There's an inner product, okay, which is equal to the omega ij is vi and wj, capital Vi, capital wj. You see, again, these components, okay, they are contravariant components, and they belong to the vector space. And the omega ij, it belongs to the dual space, dual vector space, you see? Now, the step 2, take partial derivative. You see, partial derivative of a scalar, okay, which I can represent phi as the inner product. I think it's better to write, okay, this I can set here the parentheses, no problem, because I define the inner product there. So dw, the omega ij, vi omega j. You see, here you see only dummy indices. You see, I and j are dummy, so this is scalar. Now, using the scalar product rule or Leibniz rule, I will take the derivative of this scalar here with respect to xk. So this over here, I just use the product rule. You see, you just see over here, it's quite easy, okay? The derivative of the omega ij, vi wj plus wj, this d omega I partial, the derivative with respect to xk of VI, and the last one, dij VI partial derivative with respect to xk and wj. That's using the Leibniz rule. So this, I'll stop here. I'll call this here as relation 1. You see? I will follow, okay, this derivation. Now the next would be step 3. Then you see the next lecture 15b, where Christoffel symbols will be involved. Exactly the step that I did for lecture 14 for one form. See, exactly. So that's a lecture 15a. Okay, that's it.